CAS Unit 2, Topic 8 is on energetics, and this is the first part of the specification. If you go to the glossary, here are all the definitions that you will be required to know for this topic. Enthalpy is the total thermodynamic energy in a system. The system can be the reactants or the products in a chemical reaction. Delta H is the change in enthalpy, and the units of delta H are kilojoules. For standard enthalpy changes, kilojoules per mole is used because the enthalpy change is quoted per mole of a particular substance in the reaction. If we have a look at this past paper question, we are given a positive delta H value, and the question asks us to explain using the delta H value whether the reaction is exo or endothermic. If the value is positive, it is an endothermic reaction, and if the delta H value is negative, it is an exothermic reaction. Let's look at standard enthalpy change. Standard enthalpy change are enthalpy changes for specific reactions that occur under standard conditions. Most enthalpy changes are measured in kilojoules per mole, and they are measured relative to 1 mole of a particular substance. It is important also to note that standard conditions in terms of pressure is 100 kilopascals and temperature is 298 Kelvin. Enthalpy level diagrams show the relative enthalpy of the reactants and the products together with the enthalpy change. The diagram looks different for endothermic and exothermic reactions. Because energy is released in an exothermic reaction, the enthalpy decreases from reactants to products, so the change in enthalpy is negative. If we look at the diagram for the endothermic reaction, you can see energy is taken in during an endothermic reaction, and the products are at a higher enthalpy value than the reactants. Activation energy is the minimum amount of energy required for a reaction to occur. It is important that you're able to put in activation energies on your enthalpy profile diagrams, both for an exothermic reaction and for an endothermic reaction. It's important to know how to label an enthalpy profile diagram. Here's a past paper question on labeling where the activation energy is on an enthalpy diagram. You can see they've said how a catalyst works. So obviously they're talking about the activation energy. Pause the video and have a go. We're going to start by looking at the standard enthalpy of formation, which is delta HF. The definition for the standard enthalpy of formation is the enthalpy change when 1 mole of a compound is formed from its elements under standard conditions. To make sure that you have 1 mole of a compound, you may find that you use non-whole numbers when balancing the equation. The other thing to remember is that elements in their standard states have 0 enthalpy of formation. A common question is to be able to write equations representing the standard enthalpies of formation. You might want to pause the video and have a go. In each answer, you can see that on the right-hand side, you have 1 mole of product. The other thing you will notice is that all the elements and compounds are in their standard states. So for example, hydrogen is a gas, sodium chloride is a solid. It's important that you remember to put the state symbols into the equations. The next definition we're going to look at is the standard enthalpy of combustion, which is delta HC. The definition for standard enthalpy of combustion is the enthalpy change when 1 mole of a substance is completely burnt in oxygen under standard conditions. Again, you may find non-whole numbers when you're balancing these equations so that you have 1 mole of your fuel being combusted. Again, you will be asked to write equations representing the standard enthalpies of combustion. Pause the video and have a go. Again, you can see all the elements and compounds are given in their standard states. And if you look on the left-hand side now, you can see that in each case, you have 1 mole of your fuel. Here are some multiple choice questions where you're asked to identify the equation for the standard enthalpies of formation. Pause the video and have a go. If you look at the second question, you can see that equations C and D look very similar, except ethanol is a gas in C, but a D in liquid. We would pick answer D because, of course, ethanol is a liquid under standard conditions. The standard enthalpy of neutralization is the enthalpy change when 1 mole of water is produced in a neutralization under standard conditions. This value is always exothermic and it is minus 57.9 kilojoules per mole regardless of what strong acid or strong base is used. If we have a look at the equations, you can see that all species must be in the state they would exist under standard conditions, but the reaction must show 1 mole of water produced, which may result in fractions being used to balance the equation. The next section is where we are going to look at experimentally determining enthalpy changes, and we're going to use the equation Q equals mc delta T. It is relatively easy to measure temperature changes for reactions that take place in solution, such as neutralization and metal displacement, and it's easy to measure temperature changes for combustion reactions. We're going to use the formula Q equals mc delta T. Q stands for heat energy and is measured in joules. Mass is for the mass of liquid that is going to be heated, so it is in grams. We're going to use a value for our specific heat capacity as 4.2, and the units are joules per Kelvin per gram. And we're going to measure our temperature change in Kelvin. The diagram on the slide shows the simple apparatus that can be used to measure the energy change when a liquid fuel such as ethanol is burnt. The results can be used to calculate the energy released per mole of fuel, and this is the enthalpy of combustion of the fuel. The following measurements are taken during the practical: the mass of water, the temperature rise of the water, and the loss in the mass of fuel. The water that we use is held in a copper container. You can see that on the picture on the right. Copper is used because it's a good conductor of heat and it has a low specific heat capacity. On the left-hand side, you can see a picture of the fuel burner. It is important that we weigh the fuel burner at the beginning of the experiment and at the end of the experiment because we need to be able to calculate the loss in mass of the fuel. Let's look at how we would process our practical results. The first thing we're going to do is work out our temperature change. So our temperature increased from 22 degrees to 32 degrees, and that gives us a temperature change of 10 degrees. If we look at our value for specific heat capacity of water, the units are joules per gram per Kelvin. A temperature change of 1 Kelvin is the same as a temperature change of 1 degree centigrade. That means we can use 10 in our equation. So using Q equals mc delta T, we used 100 grams of water. Our specific heat capacity is 4.2 and our temperature change was 10 Kelvin. This means the heat absorbed by the water was 4,180 joules. We're now going to look at how much fuel we used. We used 0.25 grams of ethanol and we need to convert that to moles. So that works out at 0.005435 moles of ethanol. We're now going to work out our enthalpy change. We're going to take our heat absorbed by the water and divide it by the moles of ethanol burned. That will give us an answer in joules per mole. So it's important that we divide by 1,000 to get our kilojoules per mole. Finally, don't forget that combustion is an exothermic process, so this answer is minus 761.9 kilojoules per mole. Don't forget to check in these questions if you are asked to quote the answer to a specific number of decimal places or significant figures. The enthalpy change for neutralization can be directly measured using the apparatus shown on the slide. Polystyrene cups are used as calorimeters as they are excellent insulators and have a low specific heat capacity. A common exam question is shown on the slide. So you can see the apparatus for measuring the enthalpy of neutralization, and it asks you to suggest 2 improvements to the apparatus. And these would be, first of all, using a lid to prevent heat loss, and also placing the cup in another cup or beaker, or using thicker polystyrene, again, to prevent heat loss. If we want to practically calculate the temperature change, we can plot our temperature as the reaction proceeds. The graph shows us the temperature of the reaction mixture from the point where the 2 chemicals are mixed together. If we extrapolate this line back, we can measure the accurate temperature increase. Let's look at how we would process our results. So in this case, 25 centimetres cubed 2 molar hydrochloric acid was added to 25 centimetres cubed of 2 molar sodium hydroxide. And the initial temperature was 20 degrees and the temperature increased to 33 degrees. So as before, we're going to work out our temperature change, which is 13 degrees. The total volume of the solution are the volume of the hydrochloric acid and the sodium hydroxide added together. Using MC delta T, the heat absorbed by the water is 2,730 joules of energy. If we look at our equation, we can see that we had 0.05 moles of hydrochloric acid and 0.05 moles of sodium hydroxide. That means that we produced 0.05 moles of water. To work out our enthalpy of neutralization, we divide the heat absorbed by the water by the moles of water and convert our joules per mole to kilojoules per mole. Because the temperature went up, this reaction is exothermic, so the value then becomes negative. As mentioned previously, regardless of what acid or alkali is used, the enthalpy of neutralization is minus 57.9 kilojoules per mole. That's because the ionic equation for each of these reactions is H plus ion reacting with the OH minus ion to produce 1 mole of water. If the experiment is repeated using a weak acid, such as ethanoic acid, the enthalpy change has a less exothermic value. This is because energy is required to fully ionize the weak acid, which would otherwise have been released as heat. The reaction between a weak base, such as ammonia, and a strong acid, such as hydrochloric acid, also has a less exothermic value due to the extra energy required to ensure the base is ionized.